here is a rundown of what I think about the answers to the questions we worked on in class this week regarding the controversy over the lysozyme enzyme mechanism. What is the biological role of hen egg white lysozyme? This is really just to get us grounded. Of course, lysozyme is an antibiotic molecule present in egg white and serves to maintain the sterile environment of the egg white and of the growing organism. Lysozyme digests carbohydrates that decorate the surface of lots of bacteria. We don't need to go into exactly which class of bacteria. Not so relevant for us right now, but the point being that by degrading those surface carbohydrates, the bacteria are killed effectively or destabilized at the least, and so lysozyme serves to destroy those organisms, keep them from proliferating in the egg white. I should say that egg white has a number of different antibiotic strategies, all of which are very interesting and serve together to be very effective in maintaining that sterile environment. What's a retaining glycosidase, and how do the reaction mechanisms proposed allow for distinction based on this retention? Let's look at some slides for a moment first. Let's wrap some of these questions together. The bottom line, though, is that a retaining glycosidase retains the configuration of a particular set of functional groups in the substrate molecule, as opposed to leading to, in the products, some mixture of different product molecules or different product configurations. In the mechanisms that we're going to discuss, both lead to retention of configuration, but it's worth reminding you that in a standard SN2 reaction, we do consider that to lead to an inversion of configuration, whereas we'd normally invoke an SN1 reaction if we wanted to retain the configuration. The trick with the SN2 version of the mechanism is that there's a double displacement, so we do invert the configuration briefly before returning to the original configuration in the final product. Here's some carbohydrates. I think that's relevant to our next question. Right, I'm not going to sketch N-acetyl-muramic acid, beta 1 to 4 N-acetyl-glucosamine, including all the hydrogens. And I'm not going to arrange the active sites around it. You can look at that in your textbook. It's a good exercise for you to go through that. What I want to get at with this question are the important aspects of the carbohydrate structure that help us understand what's happening in the enzyme. So if we return to the slides, here's glucose, two versions of glucose, two anomeric forms of glucose. Note that this is a 6-membered ring. The carbons that participate in this ring are tetrahedral, so we can't be planar. The oxygen here was a hydroxyl in the linear form of this carbohydrate. We'll see that in a couple of weeks, and attacks this anomeric carbon to cyclize that carbohydrate. This is the anomeric carbon. There's two ways that this anomeric carbon can be configured. Alpha is that configuration in which the hydroxyl is in this axial position. The other is beta, in which the hydroxyl is in an equatorial position. So in terms of the substrate, we can briefly look at that, and I'll come back to this in a moment. You know, what we're talking about is the relative configuration of this oxygen in the glycosidic bond. So the substrate is a beta substrate, beta 1, so the anomeric carbon here being carbon number 1. Beta configuration, 1, making a glycosidic bond between this carbon and this oxygen, and then the carbon 4 of the next monomer in the carbohydrate polymer, reminding you that the substrate is a beta 1 to 4 linked disaccharide. Hopefully that'll make sense for you. But that bond that is cleaved is that carbon-oxygen, carbon 1 of the substrate to oxygen glycosidic bond. Okay, let's think about the key similarities and differences between the proposed mechanisms. I'm going to show you those again, but in other words, what are the two intermediates that would allow distinction between SN1 and SN2 mechanisms? Why would they allow this distinction? Well, anyway, let's just look at the pictures for a second. I've broken this down. This is just straight out of your textbook, I believe. Just broken this down into the two stages of the reaction. First, looking at the SN1 reaction, what distinguishes this is Well, first let's look what doesn't distinguish it. In both the SN1 and the SN2 reactions, what we see is that the glutamic acid, which is protonated, right, alarming, a protonated glutamic acid at physiological conditions, that donates a proton to that glycosidic bond. So effectively, we add a proton across that glycosidic bond, breaking it, and then replacing that with just a standard hydroxyl. In either case, that's critical. So that is a key similarity in the reactions. Another key, before I leave that, let me just remind you that this glutamic acid should not be protonated, right? If we believe our pKa is at pH 7, this guy should be ionized, right? Negatively charged deprotonated acid. And so we discussed in class the fact that it's the configuration of the active site that leads to the elevated pKa of this acid, right? So that it retains that proton even at physiological pH, and it's just the burial in a sort of a hydrophobic pocket that drives this molecule to prefer, if you want to anthropomorphize, a protonated uncharged state. That would be more stable in a nonpolar environment. What's another similarity? Well, let's jump ahead to the end of the reaction where we add a water molecule into the active site, and now that glutamic acid, which was deprotonated in the first step, becomes reprotonated, right? Abstracting a proton from this water molecule, activating that hydroxyl, which now attacks that anomeric carbon again. So there's a variety of things that are really cool that are being illustrated by this mechanism. Of course, one is that, as I said, that weird pKa of this glutamic acid. Another is that enzyme active sites serve to be activators of some functional group or other. It can either be a functional group of the protein itself, or of a cofactor, or of another molecule. You might consider this water to be a cofactor in the enzyme mechanism, certainly a requirement. And the other key thing that it emphasizes is that in the end, the glutamic acid has returned to its original state, that is, the protonated state, so that we can again begin our reaction over again. In terms of distinguishing these two reactions, the key difference is the role of this aspartic acid 52. In the SN2 mechanism, we see now we see that the aspartic acid attacks the carbonyl of the anomeric carbon, forming a covalent intermediate. I don't know if I showed you the picture here. Yeah, okay, this is important. So we form a covalent intermediate with that anomeric carbon. We have no covalent intermediate in the SN1 mechanism. Critically as well, though, we retain our configuration, whereas here, if we attack at this carbon, then we bump off, we lose the oxygen in the glycosidic bond, and we've formed a hydroxyl between this carbon 4 of the second member of the carbohydrate polymer and that proton. So there's our covalent linkage, and we again effectively reversing, since now the aspartic acid oxygen is now in the axial position. We've inverted the configuration, right? How do we get it back? Well, we get it back by adding this hydroxyl back and knocking the aspartic acid off. So again, the distinction between the two mechanisms is that while we do retain configuration in either one, we have to go through two steps in order to recover our beta configuration in the SN2 mechanism. The other difference, of course, is that we invoke the development of this positive charge in the SN1 mechanism, and that makes this carbon a good electrophile for the attack by this guy. So let's check where we are with respect to our questions one more time. Right. So allowing for the distinction. Yeah, that's a little slippery, but the obvious answer is that you're going to look for the presence of the intermediate. And the book argues that both these structures, right, this cation and this covalent intermediate, exist for very short periods of time, or predicted to exist for very short periods of time, not observed. So the strategy, of course, is to figure out a way to stabilize this one. And I should point out that this might be the easier reaction mechanism to find evidence in support of, and we'll talk about why that is in just a moment. The other reason to look for evidence to support this reaction mechanism is that most of the other glycosidases that people have studied have the similar SN2 type mechanism. And so for this to follow an SN1 mechanism would be a bit of a departure from other mechanisms that have been observed. So maybe people would be a little more skeptical of it. Okay, next question. Sketch and annotate a rationale why an E to Q substitution should demonstrate which mechanism is right. What other processes might such a substitution affect? Well, if we mutate this glutamic acid to a glutamine, then we can't carry out the critical step, which is the attack by this hydroxyl on this anomeric carbon of the covalent intermediate, thereby lengthening the lifetime of that covalent intermediate, allowing us to observe it. And in fact, I think I can bring up a picture of crystallographic evidence for the preservation or the increased lifespan of that intermediate. Just give me a moment. Right, so now we're looking at the paper, the original paper that the review article was covering. I'm just scrolling down to the end. If you want to look for mass spectroscopic data, that's beyond our discussion. Sorry about this. Let's scroll down. There's some crystallographic information suggesting that I'm trying to look for a clear picture. Well, here we see it's a little bit difficult to see. There's two structures that are overlaid. We see a covalent linkage between ASP52 right here. I'll zoom in. Ooh, you guys are angry at me. Sorry. Let's zoom in on this crystal structure. There's our aspartic acid in the free version, and in yellow here is some other substrate that isn't covalently linked. But here, in this case, in the case where we've mutated that glutamic acid to a glutamine, we see a covalent linkage between the aspartic acid 52 and the substrate. There's that fluorine, but now I'm jumping ahead of the game. So just let's go back to our questions. Let me just remind myself what I'm supposed to be answering here. Right, so obviously what the E to Q substitution does is lengthen the lifetime of that covalent intermediate, because there's no way that the glutamine can donate a proton, abstract a proton from water, activating that hydroxyl to attack the anomeric carbon. What else does it affect? Well, obviously, it's going to affect the ability of the glutamic acid, since it's no longer glutamic acid, to donate its proton in the first place. So you could imagine that we're affecting the first step of the kinetics of the first step of the reaction with this as well. Obviously not sufficiently to stop the reaction, or else we'd never see that the formation of that covalent intermediate, as we obviously do see. So maybe it's interesting to point out here that things are a little bit sloppy in that active site. Even if we get rid of the glutamic acid, the aspartic acid is still there, and we're able to get a proton from somewhere, probably water. Right? Obviously, we're invoking water in other parts of the reaction mechanism. We can invoke one here now as well. The point being that the removal of that glutamic acid 3035, or the conversion of that to a glutamine, doesn't get rid of our key player in the mechanism, which is the aspartic acid, which acts as the nucleophile, breaking that glycosidic bond. But it is complicated, because there are other things that you alter when you, there are other steps of the reaction that you alter when you make that substitution. So 6, explain the other method the authors used to discriminate between the two mechanisms and the results. Can you show where the substrate was altered? Oh, I sure can. Let's go back to the slides. Here is a picture from their paper, and of course here they're showing you the glutamine substitution. So they're showing you the whole experiment. The paper sort of broke it up into a few different pieces. They talked about the effects of the glutamine. They talked about the effects of putting this fluorine here, which is a magnificent leaving group, right? So accelerating this step of the reaction, the formation of the covalent intermediate, and because of the relative goodness of the fluorine as a leaving group, as opposed to the second, what would be here, the second carbohydrate moiety. And then also they have a fluorine that they placed here, which again just affects the ability of this carbon to be attacked by the aspartic acid. The other important thing to note about this particular fluorine, again, electron withdrawing atom, disfavoring other reactions. This is straight out of your paper. Disfavoring reactions at that anomeric center. What would those reactions be that are disfavored? Well, attacked by this hydroxyl. So there's the point being that they have created a perfect storm of stabilization of the covalent intermediate. First of all, the glutamic acid isn't here to abstract a proton from water, activating that water. Second of all, in terms of the formation of the covalent intermediate in the first place, we've got this fluorine, which is a perfect leaving group, and then for the maintenance of that covalent intermediate, in addition to the loss of our glutamic acid, we have this fluorine that effectively slows down the hydrolysis of that covalent bond between asp52 and the anomeric carbon of the substrate. Finally, or almost finally, why does the second method leave doubts about the result? Well, suffice it to say that they've sort of guaranteed themselves the answer that they wanted to see, right? They've stabilized the intermediate, and therefore they are bound to see the intermediate. That doesn't prove that there's not another pathway that is useful or utilized in the absence of all of the manipulations that they carry out. The point, this is related to the last question, how might you stabilize that SN1 pathway? Well, you could imagine manipulating the active site in such a way that you could drive the reaction down a different kinetic path. So I guess what I would submit to you is that we could imagine that both reaction, let me come back to our slides, both reaction mechanisms are in play, perhaps, or potentially in play, and what determines whether we go through one or the other could simply be the detailed conditions under which the reaction is taking place. Now, the last question does get to this sort of, how might you stabilize the SN1 pathway? If it's really true that all we're doing is stabilizing or accelerating one pathway versus another, then how could we destabilize the SN2 pathway in favor of the SN1 pathway? And what you might imagine, naively maybe, is to simply try mutating the aspartic acid 52, right, to something else. So in that case, if you delete the aspartic acid, you're never going to form your covalent intermediate, because that is the molecule that's performing that is driving the formation of that intermediate state. Well, it's a little more complicated than that, and I wanted to read you a slide, an excerpt from the actual article in which Vocaldo et al. I think it's Vocadlo, sorry, that might be my typo, in Nature in 2001. Again, the paper you read was a review of this particular article. I'll just read it. The crucially important role of asp52 as a nucleophile is underscored by the extremely low levels of activity that hen egg white lysozyme D52N mutants have on well-defined substrates, noting there that they've mutated D52 to an asparagine. Less than 1% of wild-type activity. The considerable residual activity of hen egg white lysozyme D52 alanine mutant on complex cell wall substrates has been shown to arise from chemical rescue, wherein free carboxylate groups of the peptide moieties of the cell wall take the place of asp52. Goose egg white lysozyme GEWL, which bears some similarity to hen egg white lysozyme, lacks an equivalent to asp52 and was long considered to provide blah blah blah. So let's get back to and just say that you don't have to make the mutant. Sometimes you can find the mutants in nature, but in this case you made D52 to alanine, and we see that in fact we're still active. We delete that aspartic acid and we're still active, and that's because the substrates themselves can provide the proper the proper nucleophiles for formation of a covalent intermediate. It's interesting to note now that the covalent intermediate is not a covalent intermediate with the enzyme itself, but actually part of within the substrate. So that's a really interesting, fascinating story. I'm sure if any of you wanted to go learn about that, you could. But it's interesting to note too that it really depends on what we're working on, right? If we do well-defined substrates, right? If we take our dimeric or our disaccharide, if you will, and look at this particular mutant, we see no activity. But if we use a natural substrate, very much more complicated substrate, we do see some activity, right? Significantly enhanced activity over those sort of more controlled experimental conditions. So the point being, I guess, that we could try to stabilize the SN1 pathway by removing the aspartic acid, but when we do so under controlled conditions, we don't seem to favor that SN1 pathway to any great extent. If in fact that 0.1% of residual activity is by the SN1 pathway, that would be interesting to explore. But even so, it's still not a terribly efficient pathway, and all that experiment serves to do is to illustrate the importance of the SN2 pathway for a functional lysozyme. So let me just wrap up by saying I'm probably not going to give you another lecture on enzyme mechanism aside from this blurb, but I think that this set of questions really serves well to highlight some of the critical ideas in enzyme mechanisms. And just a brief review of whatever some of those might be. The one thing I want to mention again: manipulation of pKa's of various functional groups, right? And that has to do with the details of the chemical environment in the enzyme active site. Hydrophobic pocket, effectively driving the pKa of glutamic acid up by 3 orders of magnitude, from 4 to 7. Not only that, but we also want to highlight the importance of this glutamic acid as both a proton donor and then, in a subsequent step, a proton acceptor. Equally important for this glutamic acid to abstract a proton from water, right? And then again, too, that returns the glutamic acid to its initial state so that we can begin another round of reaction. The other thing that I want to point out, of course, is the role of activation of other molecules in enzyme mechanisms. So now we could say that in the SN2 reaction, we've sort of spent aspartic acid 52 as our nucleophile. So what are we going to do to break the covalent intermediate? Well, we can't just use the glutamic acid, because although it could act as a nucleophile, but then we'd be swapping one covalent intermediate for another. Instead, we use the glutamic acid to activate somebody else, in this case, a water molecule. And this is a very common feature. So we sort of have a ping pong of protonation, deprotonation of acids, and so glutamic acid acting as an acid and a base in a single reaction mechanism. We have the activation of other cofactors or co-substrates, if you will. We have the importance of electronegative atoms, even though this is a sort of a manipulation, electronegative atoms in defining reaction kinetics, because of course what we're really talking about manipulating here is the reaction, different pieces of the reaction coordinate or the reaction mechanism. Yeah, so I'll leave it at that, and hope you enjoyed this blurb as much as I have, and we'll see you in class.